Thank you. Can you hear me? Yeah, all right. Thank you. I'm very happy to be here, so thank you for the invitation. And in fact, I will try to tell you two stories today. One relatively short to explain a little bit why we are here, or I am here, not you, but I am here this week or the past week, why we were in Vilnius, and then I will tell you a bit more about the story of CHEOPS, the satellite. So let me start with first thing is, I don't know how many of you know the International Astronomical Union, but at least for you students, you should know about it. And so I will say a few words just about this union. It will be brief, but you can contact me if you have any question. So the International Astronomical Union is a union of professional astronomers. It's a professional union with professional astronomers, and we're founded in 1919, so we are more than 100 years old. And the main thing we do is to try to promote and safeguard the science of astronomy. So it's our job to try to push astronomy around the world in all its aspects: research, communication, education, development, through international collaboration. So that's what we do. We also have as a responsibility, we are the official organism that names astronomical objects. So craters on the surface of planets and things, asteroids, when they get their official name, we do that. So we have a whole process to do this. We have over 13,000 individual members in this union, in over 85 national members, and the individual members are in 92 countries worldwide. And then we are structured into division, commissions, working group. I don't want to bother you too much with this. And then we have 4 offices and 2 centers. Now, as far as Lithuania is concerned, the country joined the first time in 1935, and then rejoined after independence in 1993. And currently there are 18 individual members from Lithuania in the IAU. All right, so what do? Again, we try to promote scientific exchanges and collaboration. So we have working groups. We organize 9 scientific symposia every year, 3 regional meetings over a 3-year period, and every 3 years we have a General Assembly that brings all the astronomers who want to come worldwide together. The first one was in Rome in 1922, and you see how serious they were looking at the time. No jokes. And then last one was in 2024 in Cape Town, South Africa. Next one will be next summer in Rome. And we have already set that the one in 2030 will be in Chile, in Santiago. So that is a little bit. We do give out prizes together with famous other foundations, the senior level prizes, Gruber Cosmology Prize, the Kavli Prize, and the Shaw Prize. These are things we do together with these foundations. We also have our very own IAU PhD Prize. So every division, the 9 divisions, have a PhD prize, give out a PhD prize. So for you mentors of PhD students, don't forget to propose them for a prize in their division if you believe their work is at the level for a prize. So this is a good way to do this. And then we use astronomy to do a number of other activities like outreach, education, and development. And we have a prize for these categories as well. And these prizes are given once when we have our General Assembly. Our organization, we have these 4 offices I was telling you about, and you have them a bit in historical order. The very first one is the Office of Young Astronomers that was already there in 1967. It's located in Oslo in Norway. Then there is, well, maybe not going through exactly the right order. Yeah, the Office of Astronomy for Development, that was 2011 in Cape Town. We have an office for outreach in Tokyo. And then we had the latest, the youngest addition to the club is the Office of Astronomy for Education in Heidelberg. So that is a bit. And then we have one center that we created very recently about the protection of the dark and quiet sky. We become very worried about how quickly the sky deteriorates in terms of background light and in terms of satellite crossing the images of telescopes. And so we felt that it is time to do a few things. So let me just say a few words on the different offices. The Office for Young Astronomers, basically they organize summer school workshops and things for young astronomers, where these young astronomers meet professional astronomers and have a chance to talk to each other. And that is done on a regular basis. So again, you can look it up and you know, attend one of these schools if you are interested. It's a good opportunity to build up networks among your peers that you will find later on in your career in astronomy. The IAU Office for Education, the purpose there is to, you know, help teachers, science teachers, to use astronomy in their curriculum in a way that they do not have to reinvent the wheel every time and everywhere, but we share best practices, we share material, we share things that teachers can use in their schools. And so again, you know, you're welcome. And I know that you have what's called a national contact for education here in Lithuania, and we're very happy to have her with us here. So it's not like you're discovering these things. So you're very active in this, which is great. The other two offices at the outreach is the Office of Astronomy for Development. Here it is really not developing astronomy, but it is developing economy using astronomy. So they do things like astrotourism, because this is a very trendy thing. People like to go places where the sky is dark and you can see the Milky Way and all that sort of thing. So that there is a lot of things being done, and they distribute grants to regional places. We're helping them in get started. And then we have Astronomy for Outreach. This is again trying to, you know, communicate astronomy to the people. And how do you do this? What are the best ways to do this? How is the best way to reach? And here again, you're quite active in this, and you have your own NOC, National Point of Contacts, with whom we are happy, very much happy to work. The last is the center, because again, as I mentioned, the worry about the trails of satellite in the sky, and you have a few images here of trails going through image of CHEOPS, which I'm going to talk about. And you can see that depending on where the trail is, it is a real problem. So this is very much ongoing. This is very much important. And we use the fact that the IAU is a permanent observer at the UN to try to push this thing on policymaker level as well. But it's not easy. So if you want to know more, this is the thing. You can always write to me, and this is the QR code where you can get more, or otherwise just go to iau.org and you will find our website. Okay, so now I move to the real purpose of this talk, finished with advertisement. And I will tell you the story of the CHEOPS mission. And I will explain to you why I think it is an interesting story. I hope at the end I convince you that it was interesting. I will tell you a number of things about the mission, because it is, and it was a special mission in the ESA program. And then at the end, I will show you a few examples of science that we've done with the mission, so you a little bit. All right, so let me start with this picture, very well-known picture, right? It's a famous pale blue dot picture, and what you see here is a picture of the Earth, taken from very far away. The furthest away picture from the Earth, taken at 40 astronomical unit. So an astronomical unit is a distance Earth-Sun, right? Just for those who are not astronomers. Now, it turns out that the nearest star to us is over 260,000 astronomical units away. And this is a picture taken at 40. So it illustrates the problem we have, right? What we want is really to try to find planets like this elsewhere. And then the question comes, if you have planets like this elsewhere, what makes the Earth special is life on it. And then comes the question, obviously, whether we can find life elsewhere. And the like. So you have this quote here, famous astronomer, famous outreach person that said basically, that's our home. This little speck of light here is where we all live. So it's a bit sobering, tells you that we better be modest because we're just a speck of light in the universe. So again, the question is, are there other planets like Earth somewhere in the universe? And this is a big challenge to answer. As you know, the first discovery was made in 1995, and that's not by accident. It wasn't discovered before because it's simply very difficult to detect these things. And the big challenges, why it is difficult, is simply because planets are extremely faint objects. They don't have a major energy source in their core, like stars fusing hydrogen into helium. They don't have that. And so they're very, very faint. And in fact, the planet is invisible, 1 billion times fainter than a star. In infrared, it's a little bit better. It is just 1 million times fainter. But still, that is a challenge, right? And if that were not enough, the other problem with these exoplanets is that they are very close to their star. They orbit stars. So as seen from us, they are very close. You have this faint object, 1 billion or 1 million times fainter, very close to this bright object, which is a star. And so this is very difficult to see. It's when you have a faint little light next to a car headlights, you just don't see it, right? And the stars are distant, they are light years away, and the planet are minute light away from their star. The Earth is 8 light minutes away from the sun. And the nearest star is 4.5 years, light years away. So there is this huge thing, and if you want to represent it, I have a picture here that tells you the challenge is seeing a soccer ball 60 kilometers away gives you approximately the angle that you need to resolve these objects, right? And so the big challenge is really high contrast and high resolution imaging, right? That is a big question. And this is why it took so long to discover. And actually, I would claim we haven't succeeded yet in doing this completely. I will show you. Yeah. Okay. So this is a plot. Let's see now if I can get that to work. This is a plot. You went too far. We have to go back. Okay, well, let's forget about the pointer. I'll tell you this in words. This is the diagram where you have this angle, the apparent separation in the sky. And on the y-axis, you have the contrast, right? You have the contrast. And you see on the lower left side, you have these little blue dots that are the solar system terrestrial planet. You have Earth, Mars, Venus, and Mercury. On the right-hand side, you see Saturn, Uranus, Neptune, right? And all above, these lines are different instruments, what they will capable to be doing, like the extremely large telescope, you know, ELT, you see also HST, you see the different telescopes there. And you see that none of the instrument that we have reaches down to Earth-like planets around the star like the sun, right? So none of the existing, nor of those in construction instrument, will give us the capability to resolve, to see these faint terrestrial-like planets around the nearest stars. So we need to wait for the next generation of telescopes and satellites to hope to be able to do this. But in the meantime, astronomers are clever, and they found other ways to detect planets. And as you know, one famous method is radial velocity. Now, if a planet orbits a star, both objects orbit their mutual center of gravity. So that means if the planet moves, the star moves as well. It moves less because it's much bigger, but nevertheless it moves. And so if you look at the system, you see a star moving and you see a planet moving, and they move around the center of mass, which is a little X there. Now the problem is you don't see the planet, but you still see the star moving, right? And so if you take a spectra of this star, what you will see a spectrum that shifts to the red and to the blue, depending whether the star is moving towards you or away from you. It's a Doppler effect, simply, right? And so if you plot then the shift here, you can measure the velocity. And it is a dynamical effect. So you don't see the star, but you see the influence of the, you don't see the planet, sorry, but you see the star and you see the influence of the planet onto the star. It's like, again, the image here is a sailboat on a lake. You see it moving. What do you conclude? There is wind, but you don't see the wind. But you see the sailboat moving. And so there is a force that makes it moving. And in this case, it is the planet. Right? And so you can then, the amplitude is directly giving you a measure of the mass of the planet. The bigger the mass, the more it will push and move the star. And therefore, you can see here some orders of magnitude. Jupiter moves the sun 12 meters per second, and the Earth moves the sun by 10 centimeters per second. So this is the precision in your spectrographs you need to reach if you want to detect these. And before 1995, there was no spectrograph capable of measuring radial velocity with a precision of 10 meters per second, period. And, you know, and 10 centimeters per second, we're barely getting there with espresso. We have now capability of getting towards 10 centimeters per second. So here you have the different telescopes that have contributed to this. At the top is the 1.93 meter at the Observatoire de Haute-Provence. That's where the first planet was discovered. So you don't need a 10-meter telescope to do this. You can do it with smaller telescopes. I mean, they did it with this one. And as you know, I show you in a second, they got the Nobel Prize for that. So you don't need a 10-meter to get the Nobel Prize. At the time, at least. Now, today, it's a bit more complicated. These easy things have been done. So we have here, you know, I did some statistic when I prepared this talk. There's about 1,100, bit more, exoplanet discovered by this method. So it works. And again, this method gives you the mass, because it's a dynamical effort, the motion that are induced. And this has earned Michel Mayor in the center and Didier Queloz to the right, Nobel Prize in Physics at the time. And you can see how over time the precision of the radial velocity improved with time. And you can see that by the time it reaches about 10 meters per second, this is when they discovered the first exoplanet, which turned out to be an object that's about half the size of Jupiter. But the surprising thing is that And that's where you can a little bit see the problem with theorists. That in 1995, theorists published several papers saying, there is no giant, we have this solar system where you have the little planets, rocky ones close to the sun, the big giant ones further out. And so Jupiter has a 10-year period. And so everybody expected that any big planet that can be detected with this kind of velocity would have long period because it's far away. So everybody came back down from the observatory with their magnetic tape, with their data, and thought, well, I have 10 years to analyze before I get anywhere, so I'm in no hurry. But then the first one discovered was 4.5-day period. And at the time, nobody thought that it would be possible to have a gaseous planet, a gas ball, so close to the star. It would evaporate, it would do whatever, you would never be able to form it there, and so on. And so that was the big surprise, right? The first planet ever, we knew we had something wrong in the theory of formation of planet. One object was enough to tell us there was something deeply wrong. Anyway, so that's enough for radial velocity. The other one is a transit detection, and that is when the planet moves in front of the star, and by doing so, it hides a little bit of the surface, and therefore the light of the star decreases a little bit because of that. But you can see here is Venus transiting in front of the sun. You see how small Venus is? So the amount of light that decreases is very, very small for a planet of the size of Venus. And so you need, again, here, incredible precision in photometry to be able to measure this little drop of light due to the passage of an Earth-like or Venus-like planet. If a Jupiter goes in front, we'll see that it's much better. So here it is schematically, you are a planet orbiting a star, and if you monitor the intensity of the light of the star, when the planet goes in front of it, boop, it creates a little dip. And that tells you that there is a planet, and the depth of this dip tells you something, not about the mass, but about the size of the object. Because the bigger the object, the bigger amount of surface will be covered, and the bigger the decrease in light. And here again, Jupiter produces a 1% decrease in light, so that you can see from the ground, the equivalent. And the Earth is a 0.01%. And this you cannot see from the ground because of the atmosphere. You have to go to space to see this. Okay, so here are the different missions that have been flown or will be flown soon. In the case of Plato, that have discovered, that have used this method to discover these things. So now we have over almost 48,000, not 48, 4,800 of these objects. Last time I looked at the census. And again, here you don't measure the mass, but you measure the radius. Then you can be a bit more clever in these things. You have a star and you have the planet going around. But you see, when the planet is in front of the star, it hides a little bit, the luminosity decreases. But when it goes in the back, you for a while have a planet that's illuminated by the star, and that reflection of the light of the star adds to the total luminosity of the system. And when the planet disappears behind the star, the light decreases again a little bit. So that's called an occultation, right? But the amount it increases while you see the reflection tells you something about the albedo of the atmosphere of the planet. So you have a way to measure characteristics of the atmosphere of a planet, not just its size, but you can get some information about the albedo of the planet, which is a measure of how reflective, clouds, no cloud, and that sort of thing in the atmosphere of the planet. So just sort of think about it, right? We can say all these things, size, mass, the albedo, for an object we haven't seen. We haven't seen. It's just indirectly we can determine all these things, but we haven't yet seen them. And we will need to see them in order to make spectra. And that's the next step, is to take spectra, of course, because then you can analyze the component, you can know chemical composition, you can do a lot of things. So high precision photometry can help you do much more than just the size thing. And so here's how the discovery goes as a function of time. And you can see that these things are really exploding right now. And the method most successful in finding new objects is this transit method, even though at the beginning it was just radial velocity. So that is the major thing. And the good thing about when you have mass and density, you can compute, if you have mass and radius, you can compute mean density. And when you have mean density, it tells you something about whether the planet is a small rocky object, like our own Mars, Venus, and Earth, etc., or if it's a gaseous planet like Jupiter and Saturn, or if it's some intermediate ice ball with an atmosphere around it, like Uranus and Neptune. So you can really get sort of, again, a first step in a physical characterization. It's by far not enough. We want much more, but that's the first thing we can do, pending getting images and spectra of all these things. So the bottom line of all this introduction is to tell you that the story about exoplanets so far has been a story of measuring radial velocity and photometric value to a very high precision. And this precision was not, we could not read this precision before having developed the instrumentation to that level. And so it's also a story of technological development. So here's an exoplanet space mission catalog from a plot from ESA. And you have on the top row, you have missions that are completely dedicated to exoplanet. And on the bottom row, you have the sort of the multi-purpose missions like Gaia and JWST and these sorts of things. So, and among those is this little CHEOPS here. And this is a photometric mission. So we measure the light of the star to a very high precision. And it is really the first time this was done for various reasons, from a technology point of view, as much as a science point of view. From a technology point of view is it was ESA created for the first time in 2012, the so-called small mission program. And they defined a small mission as something that costs less than 50 million euro to ESA, and that would be developed and flown in less than 5 years. So that is the idea. And so they had the call, and the number of proposals were turned in, and CHEOPS came out as the winner of the competition, and so we started building CHEOPS. So in the end, CHEOPS costed a total about 100 million euros. Again, 50 came from ESA, and the other 50 were raised between the different countries, part of the CHEOPS consortium. I will show you in a second where this came. And again, it had to be a 5-year development time, so it was no time to develop fancy new technology. You had to take things almost off the shelf, not quite, but almost, to do that relatively fast. And scientifically, it's also a first, because that's the first mission that was not about discovering new planets, but it was about going back to those we know already, but for which we do not have enough precision. We wanted higher precision, higher photometric precision. And so it is a follow-up mission. So basically, our idea was not to discover new planet, but our idea was to refine the ones. In particular, you have things like ephemerides. If you lose the time of the transit, it's very hard to ask for JWST time or any big infrastructure time when you don't know when it happens. These things are so precious that you have to be very precise when you want the time. You cannot say, well, I'll use it the next 2 weeks. That doesn't work like that. So we had to go back and do a certain number of things. And so we had a whole bunch of science cases that we believed we could do, and among others is to provide these golden targets to future bigger infrastructure. So we make big infrastructure more efficient in a sense because we tell them exactly where and how and when to look. So CHEOPS being this follow-up thing is really this interface. That's why I call this an interface mission, because you have it's a follow-up, so you need to take data somewhere, right? We're not searching for something, we're following up. So we need input data. And so we take all sorts of input data from ground-based radial velocity survey, from ground-based transit survey, and what has turned quite productive is from TESS. TESS is a much smaller telescope than we are, but they are very good at discovering because they look at plenty of the whole sky pretty much. And so they provide us targets we follow later on. And what we do then, we gave the target then further away to further studies, spectroscopic studies by HST or JWST, and later when flown ARIEL or the ELTs. So that is the key on this thing. So on this side, you have the discovery part, and on this side, you have the characterization part. And so this is this interface concept that I was trying to tell you about. Okay, so that you get a little feeling about how all this works. Here's a timeline and milestones. You have different component of a mission. You have the instrument, you have the satellite itself, and you have the ground segment. And all of that you need to organize. And this is what we did. It was selected in the fall of 2012 by ESA. It was then adopted after preliminary studies to see that it is really doable. We selected the prime, which was Airbus, Spain. We selected the rocket much later, and that was a major problem because we had to design a lot of these things in a way that they fitted in all fairings of all possible rockets, regardless of vibration, size, and whatever. So we had to design something that was very compact and very solid so they can withstand a lot of vibration. Then the instrument was delivered, the spacecraft was ready, and we had to put it in storage because we were a passenger, secondary passenger in the launch in a rocket, and the prime passenger was not ready, so we had to wait for him to be ready so that we can go. And then finally we launched at the end of 2019, and we went to Spain to prepare it, and we returned home in end of February, and then there was a lockdown, COVID, right? And so within 1 week, we could finish the preparation, the commissioning. 1 week more, and CHEOPS would have turned 2 years in space doing nothing because the commissioning wasn't finished. So, that was really a piece of luck we had there to finish just on time before the lockdown. Then we could operate it from home. We were using this satellite from home during the lockdown. And what's surprising, maybe a bit in this rocketry, is that was completed on schedule and within budget. So that doesn't happen too often when you develop this satellite. The organization who did what, you can see here on the payload and the satellite. ESA mainly produced the platform with Airbus in Spain. Science operation, and you see the different different countries involved. Switzerland was everywhere. We were the prime, sort of the PI ship was in Switzerland. And we had help from Austria, Belgium, Germany, Hungary, and Italy on the hardware. and on the operation, France, Portugal, Sweden, and the UK. And on the operation, the ground segment, the antenna, receiving and sending things was in Spain. And so here's how it looks. It's a strange-looking object. It's a hexagonal base, and on top you have a single instrument, the telescope, and you have the solar panels are in the back. And so CHEOPS always fly with its back against the sun. And so that the sun illuminates the solar panel, and the solar panel shade the radiators that you see on top of the telescope here, the purple-looking plates there. These are the radiators which we use to control the heat on the tube of the telescope and the heat on the focal plane. Because again, the whole purpose, I'll come back to that later, is precision photometry. And precision photometry, you need to minimize everything, every source of noise. Reflected light, electronic noise, noise because you have your CCD changes temperature, and all that sort of thing you need to try to minimize. And so the key challenge, the mirror itself, I'd show you, is a 30-centimeter mirror. You know, there's nothing extraordinary about a 30-centimeter mirror. But it is all the rest that you have to do that this has the optimal stability and precision was the challenge. So here you can see a little bit how this thing looked like. And once it was fully assembled, and let me show you a cutout of the payload. So again, the purpose was photometric precision. So the telescope itself is just the part in the middle here. The big gray thing to the left is just a baffle, is to prevent stray light to enter the telescope. Because if you have stray light coming in, depending on where you look, your photometric precision is ruined. So you had to, and that's also why there were little vein inside to prevent reflecting light against the wall of everything, etc. So then you had, okay, so you have a stray of light coming in, where it comes in like this, bounces off the primary, secondary, and then it goes back to where the focal plane is. And the reason is this bend is again because we didn't know how big a fairing we would have, so we needed to make it very compact, so we had to bend it going like this. But that's the thing. So you see, and then you had this blue tube in the middle. This is again a little cone like this with a little hole so that only the focused light can get into the back-end optic and to the CCD, and that would catch all reflected light inside the tube. So anyway, that was the thing. And the CCD was a temperature controlled CCD, 10 millikelvin, and again using the radiators to try to radiate to space. And so the radiator always had to be in the shade because otherwise that would have been damaging. So that also, you know, implied that defined where we're looking at, what are our viewing angles. Here again, a bit of images of the telescope itself, which we built in Bern, assembled in Bern. And that here is we had defined before of the mission, we had defined some, criteria, performance requirement in terms of photometric precision for bright star and faint stars. And the limits are the colored lines here, and the dots are the actual measurements we made at the very beginning during commissioning. And so we actually satisfied the requirement, the photometric requirement, and you see was better than even for very bright star. It was over the 10 to 20 ppm. The stressful moment is the launch, of course. That was taken place in Kourou on a Soyuz-Fregat rocket. We, as far as I know, we were the last to be launched on a Soyuz rocket, because after that was COVID, and after that was the war in Ukraine. And ESA cut ties with Russia, and therefore there were no more European launch on Soyuz rockets. So again, sort of an interesting coincidence. The nominal mission was 3.5 years. We got the first 3-year extension, which we will finish at the end of this year. and we'll finish. And we are now in the process of trying to get another extension because the things still work as well as it did at the beginning. There's a lot of aging that can be compensated by software corrections, and so we are very happy with the results. So now, here about the orbit, just a thing, we're flying always. It's a, a polar orbit, sun synchronous, which means we always follow the day-night terminator. And we observe over the night side of the Earth. This is, again, to minimize the amount of reflected light from the Earth that comes towards the telescope. So we always look over the shadowed surface of the Earth, and we have our back turned towards the sun so that the solar panels can get the sun. And you have here, don't want to go into detail about visibility, when and what you're visible. This is the ground segment. This is, again, the countries involved. The satellite data come down to Madrid. From there, we copy them immediately to a mirror archive in Rome. Then they go from here to Geneva, where they analyzed, where you produce a scientific data product. And then you store them again in Rome. Somehow we felt Rome was very safe to store data. And then the commands are sort of started in Geneva, sent to Madrid. They check if there is no mistake, that we don't point the telescope towards the sun suddenly, for example, and then it's beamed up and we go. And we also used CHEOPS as a way to do outreach. And so we organized a drawing contest across Europe within ESA states. And we collected over 3,000 children drawings. That the purpose of the drawing was they had to draw something about planets. Or CHEOPS, preferably. So here's one they sent. I like this one, right? It looks like CHEOPS, but it has this little cord in the back where it goes back to Earth for electricity, presumably, and power. So I like that one. It's an interesting concept. But anyway, so we had this 3,000 drawing. We received even more, but we had space only for put 3,000 drawing on the satellite. And the way we did this is we engraved them all in miniature engravings on two titanium plates. And I can show you, sort of a blow-up of every single little drawing engraved on these titanium plates. We developed this method. Even a company had a patent now on how to do this. So that was interesting. And for the short story was, CHEOPS will come back down at the end of its life and burn in the atmosphere. And we had lots of discussion with ESA engineers to know whether these titanium plates will survive the entry or not. And so we had to dimension them so they will not. Then, the risk of falling somewhere. So anyway, so this was put then on the satellite. We had 2 of these on the satellite, and they flew then with CHEOPS. They're up there, and there's a web page you can go and consult, and every child can go and look where CHEOPS is and where his or her drawing is, etc. So it was a way also for us to build a fans club. So then have followers, right, to the mission. So it was interesting. And we mounted the plate while we were when the satellite was in Zurich in Switzerland. And you have here the crowd. There is a Director General of ESA that came. This is my science minister in the middle there. And then we also invited children who submitted their drawing to come check with magnifying glasses to make sure that their drawing is on the plate and things, and then we show them where this thing was put. So anyway, that was a fun part about outreach, taking advantage of having a high visibility thing to do outreach. I see that time is flying, so I have to move up a little bit. The purpose of this slide is just to tell you that there is GTO, it is GO, guest observing time on CHEOPS. Anyone can submit the proposal to ESA and get time to observe with CHEOPS. Right? You can submit the proposal and you can get time. There is a call organized by ESA competition. There is a TAC, time allocating committee. There's everything organized for people, for the community to be able to have time. There is also a director's discretionary time. If there's something urgent to be done, you can get time on CHEOPS. Good. Now, I show you a few science results. Selected one, biased ones, whatever, but I can't show you everything. So here's one about this star called Nutu-Lupi. There was 3 super-Earths being discovered in 2011 by Mayor et al. And so with 3 different periods, one with 11, one with 27, and one with 107-day period. And the inner 2, you see below, the transit light curve observed by TESS. But TESS didn't see the 107-day period. It's hard for transit because 107 days is a long period. And if you have to stare at the star for 107 days, it's a long time. You don't do much else. So they didn't see it during their time on the thing because TESS is observing not 107 days consecutively one region. So we looked at it, and we were incredibly lucky. Look at that. We got half a transit of the 107-day period. We tried to estimate things with radial velocity, and also we tried to optimize pure chance. But we could observe half a transit of the planet D. And why is it so important? Well, first of all, because Nutu-Lupi is a bright star, less than magnitude 6. And 100 days period, it's a long period. So you have a star that is not burning hot, a planet that is not burning hot. And you have it relatively close by around a very bright star. So any study you want to make, you have lots of photons. And so that is a good object to start with. Another type of things, I said, we follow up test targets. This is one interesting one. It's a fainter star, but it is TOI 178. And TESS found 3 planets. And you see the relative size with the star. And one with 6 days, another one with 9.9 days, and a third one with 10.3. And we thought, oh, this is a very interesting system because you have 2 planets that have almost the same period. What does that mean? That means that maybe these are so co-orbital planets. And that we don't know of any so far. So we thought, this is an interesting, potentially very interesting system. So we used CHEOPS and we looked at it. And this is why we built CHEOPS, to go back and looking at things that are interesting. And so we looked back at it, and no co-orbitals, but 3 more planets. Okay, looking at that, this 2 nearly equal period was just an LS in this thing. And what in the end we discovered 3 more planets, so we have 6 in total. And it is a Laplace resonance. They are in resonance, orbital resonance with each other. So this is a very interesting system. Such systems with 6 planets or more, you don't have so many out there. And they provide a very interesting constraint because this dynamical system with all this planet in resonance are very touchy dynamical system. So we were very happy to do this. So you see, CHEOPS is not built to find planets, but we still do, because if you look at the system with increased precision, you see things the other didn't see. So that's the advantage of looking back at things with higher precision. And that was the whole purpose of CHEOPS, is to go back with a higher precision. And so you can see things. And so we started then a huge campaign on this object because, with photometry, but also radial velocity to get the masses. We wanted to get the mass of all. And we did get them using espresso. And then you can start looking at this object, and we plotted sort of the mean density of these planets, because we now know the mass and the radius, as a function of the equilibrium temperature. That is a measure, that derives from how close you are to the star and that sort of thing. So you got these things, and the very surprising thing is that you see the planet D here suddenly has a much lower density. And normally you would expect a monotonic increase of planetary mean density with distance, simply because you have more cold gas, volatile element to accrete from at large distances, whereas in the center, all the volatiles may be blown away, evaporated, and things. So you expect sort of a more or less increasing thing. And this is very strange to have planet D, which you would then tell, well, it comes from outside, but how can it come here when the whole system is in this resonance? So for modelers, theorists to try to model the formation of this system, it's a very tricky system because you have these different densities in the middle. And the last example, and I finish, I'm sorry for being a bit long here, is about occultation and atmospheric characteristics. This is an occultation. So this little dip is the light of the star when the planet goes behind it. Not in front of it, but behind. So you don't see the reflected light from the planet anymore before and after, and that it creates this little dip in light. And you can, write an expression for the geometric albedo of a planet, of an object, as a function of the parameters that you can read here. And one is this depth of the occultation, how much photons are missing when the planet is behind. Right? One can have an intuition that this allows you to measure somehow how the fraction that's reflected by the planet, and that's what the albedo is. And so there is a formula, and when you can plug in the depths here, you get the geometric albedo is 0.096. Now, this is just a number, but then what you can do atmospheric simulation, you can build atmospheres, and you have here, and you compute what the model predicts for a geometric albedo, and here we have it as a function of the abundance of sodium in the atmosphere. And you have here the different bandpass of the different satellites, and we measured 0.10. The CHEOPS bandpass is here, and if you look what is the sodium abundance in the star, it's there. So we have a way of measuring that, this sodium abundance in the atmosphere of the planet is consistent with the one in the star and the normal Rayleigh scattering in the atmosphere. So you can start deriving from these things parameters. The final thing is not so much about the science, but it is sort of about the uniqueness of things. This is the first stellar occultation from space, and that was done by CHEOPS when this TNO Kourou is moving in front of a star. It also occults the star, so you have here the occultation of the thing. And you see here on the globe, you have the little dots show you where the shadow, where the occultation is visible. And you have a dot every minute. And on the side of the Earth here, you have the position of CHEOPS with, again, a scale to know how fast things are moving. So this is just to show how short a time it is where you have a chance to look at it. And that is why it hasn't happened. Since then, JWST did the same. So we were precursors. Anyway, so let me conclude here. I'll let you read it. I mean, it is the first small mission of ESA to a cost about 10% of a normal ambition. So that was quite an achievement, I think. And we stayed within the budget. It's small, so it took only 5 years to develop. So it is good. It is especially good for young, early career astronomers because in 5 years they get the science. They don't have to wait 20 years and spend a career for one mission that then blows up on launch, God forbid. But so this is a fast way of getting scientific return, these small missions. Go fast. And we delivered the science, and it is an open telescope for the community, as you know. And we are waiting eagerly to see if we get this extension for another year. Thank you for your attention.
Thank you very much. So we still have time for questions. Please raise your hand, and the microphone is here.
Okay, thanks a lot for your presentation. I would like to ask you, it is one more method for planetary detection. We call it microlensing. So what is your planetary expert? What it is future to apply this method, microlensing for planetary detection?
Mm-hmm. I haven't had the chance or the time to talk about all the detection methods. There is also direct imaging, and gravitational lensing is another one. And this is fine. This is a great method. There are cases, a little blip of light on the side of the light curve. The problem with microlensing is it's a one-time event. You cannot go back. So you detect it, but you cannot go study it later on because you don't know where it is. And so that is the thing. Nowadays, the emphasis on exoplanetary work is to do the characterization, to know what the atmosphere is made of, to know the temperature, whether there's water on the surface, whether, all these things you cannot do with gravitational lensing. But it is the other thing we want to do and want to know is to know the diversity of planets out there, have an idea of the zoo, basically, that exists, because Earth-like planets are nice, but they don't tell you the whole story. So it is good to have as many methods as possible to have a census of what is out there. And so that is where gravitation lensing is very useful. But it doesn't allow the a posteriori characterization. And that is why, say, for the moment, people focus more on method trying to get a spectrum.
Yes, please more.
Hello, thank you for your presentation. I wanted to ask about the radial velocity method. Is it possible to see if the wobble effect is due to single or multiple stars? And if so, is it possible to distinguish these effects that each planet has?
Yeah, you can see planetary systems, and you can see it, and it's relatively easy using the radial velocity measurement to distinguish them, because planets are not all on the same radius, the distance to the star. They are, like the solar system, you have Mercury, Venus, Earth, but they are all separated in space. And because they are separated in space, they also go around the sun at different take different period to go around, and go around with different velocity. The Keplerian velocity at 1 AU is not the same as at Jupiter's place. And so what you have, if you have one star that does a radial velocity like this, like a sinusoidal, if you have a faster one, a closer one to the sun, you will, on top of this sinus curve, you will have another little sinus curve following the big one. And so you have these hierarchical periodic functions on top of each other. So then if you have enough data, you can distinguish the different period. Then you do a periodogram, you do a Fourier transform, and you can find the frequencies, the different frequencies that are in there. You just need, the more planets there are, the more of this curve, the more data you need. So you need to spend quite a big amount of time on the telescope and getting this precise radial velocity. But in the end, if you have enough of them, you can. Physically, you can separate.
Yes, one more here, and in front.
hello, the 5 years is quite amazing to develop something like this, but how long did it take to convince ESA to make this? Like I don't know, I've been in a community that's been trying for many years and we're failing quite hard.
Yeah, I had a slide, but I don't have it anymore, I think. No, about the history of CHEOPS. So how we got to be where, to be an ESA mission. At first, we were very ambitious, and we wanted to have a Switzerland alone mission. So CHEOPS started as a Swiss mission, and we got money from our ministry to make a feasibility study. So we did the feasibility study of 4 or 5 months, 6 months to study if it would be feasible. And we concluded it would be feasible. And so we went back to the ministry and say, look, it is feasible and we can do it. And then they asked how much it would cost, right? And when we said it would cost 100 million, they said, oops, we cannot. We have to seek partners. So then they told us we have to find partners, we have to do this in a consortium. So then we looked out for partners, and the first partner we contacted was Austria and Sweden. Sweden because they had launched Odin not very long before, and they had very successful thing, and Austria because one of the main prime contractor in Switzerland has a company in Austria. So this was sort of, industrial relations that made us go that way. But in the end, the Austrians and the Swedes thought they had other priorities. They didn't want to do this. And so we were left there. And then precisely at this time, ESA started to discuss about small missions because they felt that there's a certain number of ESA member countries that are too small or too medium, if you want, to be leading a normal M or L mission. But they had enough potential that they could do something, and they wanted to do something. So the ESA science program came up with this idea of having a small mission program where individual member states could propose and try to lead such a mission. And that was announced in 2012, and they issued the call shortly thereafter. And since we had this feasibility study in our drawer, we were immediately able to get out the paper, then the proposal, and that's how we proposed, and that's how he came. So it was not as straightforward. And we were lucky that ESA, it happened at a time when ESA considered doing this small mission. Now it doesn't call small mission anymore. They have changed it because they found out of our experience with CHEOPS and this business of saying we didn't know the rocket to launch and things and we had to over-design everything. They call it FAST. They don't have the small missions, but they have now a program calling it FAST mission. Many things are in common, but now the launcher is defined. There is a bit more money in there. It's no longer 50, but 150, and the like. At the time when we did it, the word was, when we plot the budget as a function of time, we don't want to see the small mission. The budget has to be smaller than the thickness of the line of of the plot. So that was the thing. Now it's a bit bigger. Yeah, you see them, but it is a bit different.
I think it's time for final question. Yes, please.
So congratulations for the success of your space missions and that you initiated it. And our last question will be, if we have a star with 6 exoplanets, which method is most useful in order to investigate exoplanets?
Well, for the moment, we cannot. I mean, ideally is, again, the dream of all astronomers in this business is to get an image where you have a point of light somewhere that you can then make a spectra of. And all we can do, everything we know about the universe, we know it about spectra from spectra, composition and things, dynamics, Doppler effect and all this. All the information is carried from light. And now in recent days, it's a bit more. We have neutrinos, we have gravity waves, we have this different ways, multi-messenger astronomy. Now, but most of our history as astronomers is based on analyzing spectroscopy of light. And so the dream is to do this. Now, we don't get that, but people have been very clever in doing this transit spectrometry. In fact, when you have the planet passing in front of the star, you won't believe it that it works, but it does work. When you have a planet passing in front of the star, a little bit, and hiding, sending in the shadow, a little bit of the light of the star goes through the planet's atmosphere on the edge. And light going through the atmospheric medium, you will have absorption depending on the composition of this atmosphere. So you will see in the light, in the transmitted light through the atmosphere of the planet, you will see spectroscopic signature from the atmospheric chemical composition of the planet. And so that one can do nowadays. This exists. JWST does that. Ground-based telescopes do that. And not as good as JWST. JWST is really a revolution in this business. So that is the best we can do now. But it's still limited. What we can never do is to do things, we will only be able to see what's in the atmosphere, the effect, whether in emission, infrared emission of the planet, thermal emission or reflection. We can only analyze spectroscopically the planet, atmosphere. You cannot investigate what's underground. If you have a worm living underground on that planet, you will never detect it. But you can detect anything that affects the atmosphere, the composition of the atmosphere. This is what's remotely detectable. And this is what we try to build instruments to do this.
Let's thank again
Thank you.
the speaker.
Hello, so my name is Gedmanis Elertas. I was a scientist recently, half a year ago, and I'm still a scientist physicist. I worked in the atom interferometer field, which is quantum optics device in UK. And I moved back to Lithuania to work for Astrolite as an optics engineer. So I'm gonna tell my experience, because this is student event, of moving from academia to corporate life. And and how is that going? And a bit I'm gonna present the Astrolite, of course, too. So Astrolite is a Lithuanian startup. We have office in Denmark. I'll explain why is that as well. And we work with all the major European partners. And particularly, we have strong connections to Vilnius Tech University and Lithuanian Navy. So that's the corporate stuff. And moving on to the cool things. Our main product and our idea is to make an optical communication network connecting space, land, and sea. Our main product right now is the optical terminal that works in the low Earth orbit satellite and beams the data down to the optical ground station that we also make and sell here at Vilnius. And these stations, we have one currently in operation in Greece, and we are making another one in Greenland. We work with Lithuanian Navy to produce Polaris, a very successful device, optical station that connects naval vessels to ground, to ports, and provides safe, reliable data transfer between the ships. And the final project, I'm working currently, is Atlas X, and that's a bigger, much more capable space terminal that is mounted on a gimbal which means that it will no longer need a satellite to point us to the direction of communication, but it will be able to point itself up, and this terminal will be able to be mounted on a bigger satellite than the CubeSats that we're currently worked on. So that's our pathway. These are our main products and projects that we're working on. And so I would like to explain a little bit of my experience moving from academia to industry, and how I found it working at Astrolight. And I'm particularly surprised that there is such a cool company in Lithuania that I can apply my knowledge that I worked for many years in the quantum optics laboratory. So I gained lots of experience handling optics, oscilloscopes, spectrum analyzers, collaborating in bigger projects so I was a team building the largest atom interferometer in the world as well. And I was a bit worried moving from being a scientist to industry, but my worries were not materialized, and my all knowledge very smoothly transferred to work at Astrolight, because Astrolight does very hands-on building a device that requires all the components that I have worked in the lab, but now moving them outside the lab, which is a big challenge. However, it's a great fun, because we get to work at the cool location. So there is a video, I'll try to play it, and it's a bit of a headache to launch. So we'll see how that goes. To show, so my colleagues went to upgrade. So that thing that you saw is commercially available. Okay. Oh, commercially available. This is trippy. Okay. I'll go through the slides. Okay, so that's a telescope that you can buy off the market. Astrolight attaches our magic to it to essentially guide the light into the optics fiber, and then we use our skills to, we use that light to transfer the data essentially between space and ground. And we can also send the data to space via the same device. So this one is on top of mountain in Greece. As you can see, it's lots of hands-on. So here my colleagues are upgrading this device. We have to build this in the lab, test it, prototype it. We have the full chain. It starts usually on just a drawing board, just like an experiment would start. So if you are a student, it's very similar like designing your own experiment. Sometimes you don't get to do that as a student, but occasionally you do. So very similar, and then you progress through the experiment. Usually as a student you join in some parts and do some parts of the experiment, but here you get to see and work with people that do a whole range of stuff. So initially there's my optics colleague, and here is my programmer engineer who makes these device work on computer, which is great to have a whole team doing this sort of stuff. And scientists, you have to do it all yourself. So that's another great thing of working at in industry versus working in academia, that you get to work with different people, mechanical engineers, optics engineers, software developers, commercial people as well. So, okay, so let's move on, somehow go back to the slides. Maybe we can just go here. So I wanted to show what's inside the Atlas terminal. So this is the Atlas 1 terminal, and as you can see, it's a very cramped device. It's for the CubeSat, so it's quite small. This requires very clever engineering. So I am participating in the second Atlas X terminal production, so it's going to be a bit bigger, but still we have to work hard and think very carefully about things that normally you don't get to think in your typical laboratory, like vibrations. It has to survive the rocket launch. big temperature range, which is a big headache, and so this limits your choice of materials. So there's a lot of learning in that front, and as you can see, there is a lot of electronics. So people who can do FPGA programming, they are probably most marketable people on the planet, I believe. So anyways, we also make our own laser amplifiers. So there's on the second unit that houses the amplifier and the FPGA modem. And that's all done here at Vilnius in Vizore in our facilities. And yes, last month we launched our first batch of terminals to low Earth orbit, and my colleagues got a chance to see the launch in California. And here are the cool pictures. So on the top one, it's hard to see, but you'll have to trust me because I have to trust my colleagues as well, saying that this is the moment our terminals got kicked from this motherboard, I don't know how to explain it, into operational orbit. So yeah, so if you want to join us or have a chat, or if you're interested in quantum optics and the experience of being scientists in UK and working in this field, please contact me. And feel free to drop us an email, or we can arrange a tour or visit to Astrolite. We're always looking for people, of course. And yes, have a nose at our website. This is how I found the job as well. Astrolite is very good at advertising. So my colleagues in the UK were like, oh, there's this cool Lithuanian company on news on the BBC. Somehow we got an article on BBC. That was very cool. And I was like, oh, okay. And at that point, our grant was running over, so I needed to find a job, and there was the job. So very good, very successful. And yeah, thank you. If you have any questions, feel free to contact me.